thank you very much, Wolfgang. Thank you, Christian, for introducing me. And it's really a pleasure to be here. And I'm going to talk to you for the next 25 minutes or so about this book, which was published by the OECD, which was released in May, The Next Production Revolution. We were tasked by OECD member countries to examine the impacts of new production technologies economically and in terms of their policy implications. And this set us immediately the task of, well, how do you approach this issue of the future of production? Because there's a range of broader conditions, so-called megatrends, which will affect what production looks like in the future. So environmental conditions, for example, will increase pressure for materials, water, and energy-efficient production. Demographics will influence which products are demanded by consumers and where production is located. We chose with this work to take a technology-specific angle and to examine the impacts of 5 families of technology which are likely to be significant in the medium term, say up to about 2030. So we're looking at 3D printing, at digital technologies broadly defined, at industrial biotech, at new materials, and at nanotechnology. And all of this occurs against the major background consideration of the decline in the rate of growth of labor productivity, the decline in the rate of growth of output per hour worked, which has been particularly marked since the end of the financial crisis. So let's look at digital technologies first, because these really underpin the other technologies which I've been referring to. And what's really transformational about digital technology is maybe 2 things. It's not just the impact of Moore's law, the trillions-fold increase in computation you can buy per dollar, per euro, which has occurred since the end of the mechanical computing age. But it's also the combinatorial nature of digital technology which makes it so transformational. So it's the combination of new sensors, big data analysis, cloud computing, the Internet of Things, and artificial intelligence, which is giving rise to increasingly autonomous and intelligent systems and machines. I mentioned the importance of the productivity issue. What do we know about the impacts in production of digital technologies? Well, there have been a variety of firm-level and technology-specific studies, a small selection here. So we find work done at MIT in particular, illustrating that output and productivity in US firms that adopt data-driven decision-making are 5 to 6% higher than expected given those firms' investments in the hardware, in ICT. The Internet of Things reduces costs amongst industrial adopters by about 18% on average, and work done at the Oxford Martin School has shown that autonomous mine haulage trucks, that self-driving mine haulage vehicles, could increase output by 15 to 20%, lower fuel consumption significantly, and reduce maintenance costs by about 8%. A point I like to emphasize, however, is the variety of channels through which the productivity effects are likely to occur. So, for instance, intelligent systems could almost entirely eliminate errors in some production processes. And among other reasons, this is because sensors allow every item that's being produced to be monitored. Every item can be monitored, rather than having to test for errors in samples drawn from batches. In the area of artificial intelligence, General Electric, for instance, is fitting wind turbines in wind farms with AI so that the individual turbine orients itself to the wind, such that not only does it maximize its individual power generation, but it takes into account the effect of the backdraft from that individual turbine on all of the other turbines in the farm. So there's a collective dynamic optimization process occurring. The French gas company Air Liquide has millions of gas canisters around the globe which are connected to the company and which tell the company how full or empty the canisters are and when the canisters need to be maintained. Many surveyed industrialists tell us that one of the most impactful technologies which they foresee in the medium term is predictive analytics. It's the ability to maintain, on the basis of predictions, to maintain in a predictive way rather than having to maintain as a consequence of breakdowns. Some of the effects, the productivity effects of the new technologies result from really interesting novel synergies amongst the technologies. So you see here, both of these industrial products. On the right, you have this dynamic graphic. That's a bracket which is used in a NASA spacecraft. And on the left is an aircraft bulwark partition, which is used in the Airbus A320. Now, neither of these objects were designed by a human being. Both were designed with so-called generative software. This is software which, within certain boundary conditions, throws out a first design and then, fractions of a second later, mutates in a random way a number of parameters on that first design. So at generation 2, you'd have, say, 5 designs, generation 3, 25, all occurring at electronic speed. And with each generation of design, the machine culls the least fit designs. And so you have, in a sort of Darwinian way, the production, using these technologies, of designs which can optimize strength to weight ratios, which are sometimes counterintuitive. A human designer wouldn't have thought of these particular forms. If you look up close at this bulwark partition on the left, it has an almost fractal design close up, which is hard for a human designer to have imagined. And yet, that bulwark partition takes 500 kilos out of the weight of the Airbus A320. It's stronger than the partition that it replaced, and yet much lighter. Again, designed by a machine, but the point about synergy between technologies is that these generative software often yield designs which are so complex they can only be manufactured with 3D printing. So it's the combination of 3D printing and the software which is yielding the interesting outcomes. A point which cuts across many of the chapters in the book is the expanding criticality of supercomputing, which is being used in a very wide range of sectors, from aeronautics to construction to pharmaceuticals. Indeed, 2/3 of US-based companies that use high-performance computing say that increased performance of computational models is a matter of competitive survival. You have here a very practical illustration of this in the aeronautics sector, where supercomputers are used, amongst other uses, for the simulation of the designs, including designs of wings. Airbus, in fact, owns 3 of the fastest supercomputers in the world. And you see here Boeing on the left, when it designed the 767 in the 1980s, it actually had to build 77 physical prototype wings before arriving at a design that it considered was right. Whereas here, on the other side, with the more recent Dreamliner, the 787, because of the use of supercomputing and simulation, the company only had to make 11 physical prototypes. So a big productivity hit. Now, there's a broad range of policy issues that governments need to be cognizant of with respect to digital technologies. So an important issue is, and I've just touched here, just as a small number of these. So governments have to broaden access to critical ICT infrastructures. And it's not just a question of rolling out broadband. When machines are operating with tiny latency periods, just in terms of milliseconds, these machines, just bounded by the speed of light, they have to operate within a relatively small distance from the servers, say within 30 kilometers. A little bit like how in financial services you see that financial services firms which are engaged in automated trading, when they're buying a place to work from, say in the City of London, they will buy that building by the number of meters distant that the building is from the servers. Goldman Sachs paid tens of millions of dollars just to cut 4 milliseconds off the time it takes data to transit between New York and Chicago. It has its own transatlantic cable. In a similar way, firms which are dealing with very high-tech, fast-operating machinery will need to be operating in regions with high server density, rapid broadband speeds. This poses challenges for lagging regions. It poses challenges for developing countries. Governments need to reduce barriers to diffusion. We'll talk more about that in a moment, to increase interoperability, so to help develop the standards, to promote the standards development work that will allow these different technologies to talk to each other. Issues of liability and transparency and ownership will have to be addressed, and there are new issues on the horizon in this connection. So, for instance, when a contractor puts out a job to a subcontractor, let's say the contractor is buying ball bearings. In the world until now, the contractor has just bought the physical object, the material object, the ball bearings. But in order to fully make use of the efficiency possibilities provided by the digital technology, increasingly the subcontractor will not just have to provide to make the physical object, the ball bearing. The company, the subcontractor, will also have to provide a digital twin, a data file that provides information on a whole range of performance parameters about the ball bearing, the material it was made from, the manufacturing process, its tolerances of certain stresses, etc. So a data sovereignty question arises to who owns those data, who will own those data. Will the contracting firm be able to sell those data onto a competitor of the subcontractor or use the data itself to generate value? We don't have a legal framework yet to fully wrestle with this question, and that would be one of the emerging policy issues that governments need to address. Digital security, of course, is essential, not just cybersecurity and the theft of intellectual property and critical industry data, but also issues around the overall integrity of digitally linked systems linked through a digital thread. So the next technology then is 3D printing, and clearly there have been many innovations in this field in recent decades. Printers have gotten smaller, they've gotten less expensive, they've gotten faster. It's now possible to print with over 500 different materials, from plastics, metals, even glass, even printing human tissue down to a resolution of individual cells. So we see, however, 3D printing everywhere. You know, it's on the front of Time magazine, The Economist, etc. The impression is given that 3D printing is revolutionizing production. And so the question arises, how widespread will 3D printing become in manufacturing? It's true that much machining work today is being replaced with 3D printing. So Boeing has replaced hundreds of parts with 3D printed equivalents. When I say machining, I just mean taking a material, usually a metal, from which you abrade or cut or remove some part of its mass. When you see a metal piece spinning on a lathe and having material extracted from it, that's a machining process. So much machining work will be done by 3D printers, but machining actually only represents a small part of manufacturing, about 5% of total value of manufacturing. And when you look at a cost curve comparing 3D printing with existing mass production technology like injection molding, then with large levels of output, 3D printing is not yet cost competitive. But this cost line, this flat cost line, is lowering all the time. Gradually, the technology is becoming more competitive as the machines get more efficient in terms of the use of energy and actually can print faster. One of the issues we've been looking at in some detail here is the environmental implications of 3D printing. It's the popular press often holds that 3D printing will be environmentally benign, in part because it's not subtractive, it's an additive form of manufacturing. But our colleagues who've been working on this for a variety of reasons don't think that will be an important benefit. There will be other environmental impacts, so you'll be able to make products using materials other than plastics, so products which had shapes which previously could only be made using plastics, but which will now be possible to manufacture with more environmentally benign materials. A variety of things that governments can do in the 3D printing space. They can help create certification systems as to the environmental sustainability of printers. They can help remove intellectual property barriers, allowing an environmental benefit which hasn't much really been talked about, which is that many of our products that we put into the waste stream, say your washing machine goes wrong. The washing machine may no longer be manufactured, but you only throw it away because one part is broken. What if you had something like a universal online database of spare parts and you could just print those parts out? That's wholly feasible technically, but the rights payments issues have to be resolved. There's a group at Aalto University in Finland which is working on this right now. So a variety of things governments can do there. The tools also exist today to begin a bio-based revolution in production, so bio-based batteries, artificial photosynthesis, microorganisms that produce biofuels are just some among the recent breakthroughs. Indeed, at the beginning of this year, scientists in Australia were able to synthesize graphene, this wonder material that's 200 times stronger than steel and as electrically conductive as copper, they were able to synthesize graphene from soybean oil. We've not been able to produce graphene in large volumes up until now for a variety of reasons. If this soybean-based process can be scaled up economically and technically, then this might be a solution to really achieving the promise that graphene holds. A variety of things that governments need to do in this area with industrial biotech. I won't go through all of them because of time, but certainly government support for risky public-private investments in advanced biorefineries is one. And we also need governments to help build the standards required around this field of bio-based processing. So we may think sort of a priori that it's got to be a better thing for the environment if we generate our energy and our chemicals and our materials from refining biomass. That biomass could be forest residue, it could be purposefully grown crops, it could be black bin, urban municipal waste. You would think then there's a closed case that this has got to be a good thing rather than mining hydrocarbons. But what when you factor in all of the energy required to fertilize, irrigate and transport that biomass, say from the rural area, then in this cradle-to-grave analysis, the calculus is not quite so clear-cut. So we need standards in order to be clear about what's good for the environment and what isn't. The penultimate of the technology we've been looking at is nanotech. There was a great deal of many expectations were created for nanotech, the work of Drexler and others in the 1980s. Its impact on industry has certainly been relatively banal to date. The largest single user of nanoparticles in France, where I live, is L'Oréal, which uses the particles in lipstick. But we think that there will be a growing array of uses. So here on the left, you see an example of a product innovation with nanotech, and on the right, a process innovation. If you think that the standard sheet of paper is about 100,000 nanometers thick, each one of the holes in this gold nanomesh is just 175 nanometers in diameter, which means that you can lay this mesh over a photovoltaic cell and light can enter but finds it hard to escape. And so the efficiency of the cell is increased. Similarly, there's a group actually a couple of months ago at Manchester University which was able to create a graphene nanomesh of a similar sort, which can physically remove salt molecules from seawater. So you could pour seawater in through the mesh and have fresh water come out the other side without additional energy input. So this is a very exciting development. And on the right, you see a process innovation where using nanotechnology, this has enabled printing at ambient temperature, room temperature, of solar cells rather than a much more energy-intensive process. There's a number of things that governments can do in this area. I'll just mention one. It's the fact that it's difficult for any individual institution or company to gather under a single roof all of the scientific instrumentation needed to make advances in the area of nanotech. Capital intensive, very skill intensive. So governments have a role here in facilitating interinstitutional and perhaps even international collaboration in nanotech related research. The last of the technology we're looking at is new materials. This is particularly interesting, I find, because it's advances in science, in growing computational power and simulation techniques, which are allowing materials scientists to create materials with entirely new properties which have not been seen before or don't exist in nature, like metals which will actually shrink when they're heated instead of expanding, or solids like these aerogels which have densities almost on a par with the density of air. The point is that simulation and data analysis has allowed material scientists to build the desired qualities into materials ab initio through understanding of their microstructure. So you can have a material and along its entire length you can make its properties, say of corrosiveness or strength or of electrical conductivity. Those properties can be made deliberately to alter along the length of the material. This means that engineers in the near future will not only be designing the products they're looking for, they'll be designing the materials they want those products to be made from. This also means that this will be a major source of competitive differentiation for firms. So if you're an automotive company and you have a particularly efficient engine, for instance, your competitive standing is much stronger if you also own the materials, the type of materials from which that engine is made. But these new materials do raise new policy concerns. One of them, interestingly enough, is new cybersecurity risks. If we have a computation-based pipeline for the production of new materials, could that pipeline be hacked? Could it be that we have this phenomenon of materials malware, malintentioned individuals who deliberately introduce design flaws into the substance of the products which are being made? Let's have a look at some of the cross-cutting issues then. One is that governments need to be attentive to and implement sound science and R&D policies. Many of these next production revolution technologies are deeply linked to advances in knowledge and advances in scientific instrumentation. And the policy issues here are many, from the size of public R&D budgets to how those budgets are allocated and evaluated. Public funding, in fact, has kept artificial intelligence research moving forward for decades, to the point now where private firms are making huge investments in AI, but it's been the public sector which has kept that research going through the various AI winters experienced since the end of the Second World War. The CRISPR-Cas9 gene editing technology depicted here in the diagram, this is ushering in enormous change in biotechnology, and it can be traced again to an accidental discovery during publicly funded research on E. coli in the late 1980s. So it's a concern, given the importance of research, that many countries have reduced public spending on R&D. We'll get back to that. And this perhaps is one of the overarching messages of the book, which is about diffusion of the technologies, because a key point is that these technologies have more to contribute to productivity growth than they are currently contributing, in part because of a problem in diffusion. Whilst great wealth can come for companies and countries that create technology, most companies and countries will be primarily concerned with this issue as technology users. You see here, and there's many instances to illustrate this point. So, for example, let me move forward. These are second-generation robots, which are smaller, more flexible, less expensive than the first-generation robots primarily used in the automotive sector. These robots are not, they cost maybe 30 to 40,000 euros a unit. They're not prohibitively expensive for small firms. They don't require many, in some cases, almost no programming skills on the part of the users. Some of these second-generation robots simply observe and mimic the physical actions of the human operator, of the human worker. And yet you see it's large firms which use these second-generation robots much more frequently than small firms. You see, in data-intensive precision agriculture, it's the large firms use the technology more than the small firms. It's estimated, I mentioned at the beginning of the talk about the important role of supercomputing. It's estimated that only about 8% of US firms with fewer than 100 employees use supercomputers, but that the potential use is that 50% of US small-scale manufacturers, they have some potential use for using supercomputers, whether it's in prototyping, design, or even directly in production. And even for a technology like cloud computing, shown here, this is showing us the share of firms of different sizes in different countries that make use of cloud computing. Cloud computing is a technology which essentially levels the playing field between small and large firms in terms of access to computation, and yet it's the large firms which use cloud computing much more than the small firms. Indeed, Angela Merkel said at the World Economic Forum in 2015 that we have to execute quickly, otherwise those who are already leading in digital will snatch the industrial production from us, and we tend to think of Germany as being the cradle of Industry 4.0, and yet, again, going to the diffusion question, a survey of 4,500 German firms in 2015 showed that only 18% of those companies were even familiar with the term Industry 4.0, and only 4% had implemented digitalized and network production processes or had plans to begin doing so. What can governments do about diffusion? Well, there are a number of things, and I'll run through these quite quickly as time is short. I spent another 5 minutes? Yep. One is that governments need to create an environment in which firms that have the ability to grow and carry new technologies forward can do so, that they can access the necessary complementary resources of finance and skills. And we see here big differences across countries in terms of the quality of the framework conditions which allow them to access these complementary resources. We can talk about that in detail. Another part of diffusion relates to the birth of new firms and their role in introducing new technologies and business models. And this role is particularly important in the ICT and biotech sectors. New firms are not linked to the legacy systems of incumbents, of those firms using existing technologies, and yet we see these aggregated data for 17 OECD economies, since 2002 in particular, quite a sharp decline in the rate of company births and quite a sharp increase in the rate of company exits. So these new firms, there's a lovely historical example, which I'll illustrate now, about the importance of new firms in introducing new forms of organization and why this matters for productivity. This comes from a famous paper, 1990, written by the Stanford academic Paul David. And this is what a factory typically looked like in the mid-1800s in the US. Stacked on multiple floors, a big steam engine downstairs, driving a whole array of equipment upstairs through these transmission systems. You got then the engine of the second industrial revolution, literally was the electric dynamo, introduced in the 1890s. The first use, though, of the electric dynamo was simply to substitute for the steam power, the source of power coming from steam. So there was no change in productivity. In fact, there was a major slowdown in industrial and aggregate productivity in both the US and UK, the largest industrial powers of the day, between 1890 and 1913. And then, in the 1920s, eventually businesses figured out that factories should be redesigned on a single floor with each piece of machinery attached to its own electric dynamo, the so-called unit drive model. The introduction of the unit drive form of arranging power transmission actually occurred in those sectors where the startup rate was fastest, in fabricated metals and transportation equipment, and on the back of a larger boom in fixed capital investment in the 1920s. And when the new business and organizational models started to be instituted, then you saw the US industry experiencing 5% per annum productivity growth. Let me just move here 2 points towards the end. One is that these technologies will also create new challenges for our intellectual property systems. We may need to rethink some aspects of patent rules, for example, in a world where machines can invent things. There are already a number of patents in the pharmaceutical sector which are based on research insights derived from machine learning. We may need to also rethink a number of aspects of the IP system as a consequence of 3D printing. You can't patent human tissue today, but what if 3D printed tissue turned out to be superior to the original? Would that be eligible for patenting? These are some of the issues which will have to be wrestled with. My last slide, I'm skipping over a great deal of information here. Perhaps we can go back to this in Q&A. But my last slide is that policy also needs long-term thinking here. Part of the reason why China is making such strides in this field is because it is adopting a multi-decade perspective on the development of digital technologies. Germany has created an Industry 4.0 steering group, and this is important, but do we see any labour ministries across Europe or the OECD preparing for driverless vehicles? I haven't seen any. And the final point is that public acceptance is also an important question. We see how public attitudes have shaped regulations on, for instance, nuclear power and GMOs, which have had the effect of conditioning the diffusion trajectory of those technologies. Might that happen with AI, with robots, nanotech, or other developments? There's a close connection between public resistance to novel technologies and the disruption of trust in public scientific and regulatory bodies. And there are many things governments can do to maintain that trust. I'll leave it there. Thank you.